Okay, perfect. Hello, everyone. Thanks so much again for joining to one of our WST 20 minutes time domain talks. And this is again one of our Synergy series. Today, we are very much delighted to host Dr. Richard Smart from INAF Torino. We majorly know him because of his significant contribution to the astrometric aspects of the huge field of substellar companions, ultra-cool dwarfs, and brown dwarfs. I knew him before because of his significant contributions to the Gaia collaborations in this field. Now I know him because of Euclid. And I have known him also because of Astronomers for Planet Earth and Enough Green. So please, Richard, take it away. The floor is yours. Thank you again for accepting our invitation today.
Thank you very much for the invitation. I must admit, I didn't know what WST was until I got invited. So I had to do quite a bit of work to try and see where there is some overlap. And for sure, I've missed some, and probably I've extended some that shouldn't be there. You can hear me okay? Yeah.
Yes, perfect.
So this is I'm looking at what can be done with UCDs and BDs with the WST, and as I've said, it's non-exhaustive, and I would almost say superficial, but and the big point about the WST is being 12 meters, and having the kind of signal to noise that it has. It can go down. I've assumed that it can go down to UCDs and brown dwarfs that can be seen by Gaia. I've made that assumption as a kind of to have a signal to noise around 30, as you will see in some of the examples that I provide. Can you go to the first slide, just in case people aren't aware of what UCDs are and brown dwarfs? UCDs are the objects going from M7 and down to around ultra-cool dwarfs down to around L3. That's where the substellar boundary is, and then starts brown dwarfs from L3 down to about Y0, and after that they're really considered planetary levels. They're very common, but very faint. So therefore, even though they're very common in the galaxy, they're probably one of the dominant contributors to the galaxy. They are one of the dominant contributions to the galaxy. In the sky, there aren't that many just because they're so faint. In the 2 billion objects in seven, so UCDs, and about 1,000, 2,000 L and T dwarfs. There's only 30 T dwarfs. In this diagram, you see the around L3 to around L3, which is where the subdwarfs are, and there's a change in color, and this is due to absorption by water bands that move the energy outside of the J band into other bands. So in this diagram, the red objects are the M dwarfs, the green objects are the L dwarfs, the brown objects are T dwarfs, and the purple objects are the Y dwarfs. And most of what you can see there, well, the Y dwarfs you won't be seen by WST, but the T dwarfs down to around 16 should be seen by 16, 17 should be high signal with a high enough signal to noise. Carry on. Next slide. So some of the pros and cons of UCDs: they live for a whole time, and all the UCDs and brown dwarfs that have been born are still alive, or still cooling, still releasing energy or cooling. They're very interesting atmospheres and physics because there are lots of molecular bands and such like. They're not just hydrogen as you get in stars. Very common, and this diagram shows with my dotted line, which I put on with a mouse this morning, shows that there is a mass radius minimum and mass luminosity, whatever you want on the here I have effective temperature and radius, but I could have put mass and luminosity. What you basically see is you see the stars going down, and when it becomes a brown dwarf, so after the substellar, can you see my mouse? No, you can't, obviously. So we're around about 2,000, 2,100. There is a turnaround where the substellar boundary starts, and because of the physics being different inside the atmosphere, they get slightly larger. So the radius gets slightly larger. This is could be used, for example, as a distance indicator if we manage to find it, and it can be used as a mass indicator as well, as we will see. Go ahead, next slide. They cool with time. Here we have the Bailey 2014 version of a Burrows plot that shows how stars cool over time. So they basically stay around the same temperature after about 1 gigayear. Brown dwarfs and planets as well, they tend to cool very quickly over the first half a gigayear or 200 megayears, and then they slowly become straight after about 1 gigayear, 2 gigayears. So this is the pro is that these brown dwarfs cool with time, or the what you call dwarfs as well. So a mid-L dwarf, depending on how old it is, could be a planet, could be a brown dwarf, or could be actually a star. So if you think about drawing a line directly from 2000 straight across, you see that a very young, when it's very young, it would be it could be a planet. We don't know. It depends on its mass. As you go around to 0.1 gigayears, it will be a brown. It could be a brown dwarf, and if it's very old, then it is a star. So there is a change of spectral type over time, and this is a pro. Brown dwarfs cool with time. But that means that spectral type degenerate with mass, temperature, and age. So whereas a star, if you know its spectral type, you roughly know its mass and its temperature. With a brown dwarf, you don't need the age. So one of the cons of brown dwarfs is they cool with time. So it's a pro and it's a con. Go ahead, next slide. So with the WST, what's very good about the WST is one, it goes from the red optical to the NIR, so it exploits, which is very very useful for ground dwarfs because they change very much over those. It's not just the Rayleigh-Taylor tail. It actually changes over the NIR over the cool area. They are very sparse, as I said. There's probably about 100,000 at the Gaia level. So if you just as they are close, they are pretty uniform over the sky. So in any given WS field, a 10 degrees field, you do the calculation, you'll find that there's about 20 or so objects in any pointing, as it were. So it's not gonna run out all of the WST fibers, but it could be very useful as a piggyback kind of project when you're looking at other parts of the other objects. You can throw in the 20 or so ultra-cool dwarfs or brown dwarfs that are in there. Three of the topics that I looked at were rotation rate and lithium information and large-scale UCD, BC brown dwarf companion compilations. So the next slide, next couple of slides, I'm going to talk about rotation rates. If we want to go to the next slide. So this is the rotation rate, how it varies with time or with age for the UCDs, for the M7s, so the 0.1 to 0.35 solar masses. And as you can see, there's a very large spread. The lines at the bottom, the objects at the bottom are various clusters. They looked at the rotations of these objects in various clusters, which have various ages. So therefore, they can look for variations. There's a growth and a drop as the objects get older. There's a large spread, and the lines are models, various models, which right now they can't tie them down with. This is one area where using the WST might be useful, because if we choose the clusters correctly, so they're not too far away, so therefore the WST can see most of the at least the UCDs, if not all of the brown dwarfs, then we will get more than 20 per pointing, because there's a joining, there's a concentration of these objects. Um, next slide, please. If we now look at the brown dwarfs, right now there isn't a lot of work on the brown dwarfs, but there are a couple of clusters where the rotation has been measured, and there is the field where the rotation has been measured, and there is a prediction of how the rotation is how the rotation period will change with age over the interim part. So this line going down is the models. Next slide. This is a proposal we put together to try and look at the variation with time. So we were going to look at these 7 or 8 clusters, and we calculated that you needed about 5 nights per cluster to measure the change in photometry for the rotation. Now, this is probably something that's going to be done by the LSST, but having said that, it is also on a quite a short scale where the LSST doesn't actually cover as well as a pointed program. So therefore, we could think about looking for the variation in the spectra with the WST, but we could also think about doing photometry, just integrating over the spectra for a study of any cluster. So we would have to look at the cluster at sample it at quite short intervals for 5 nights. That's we could probably switch between 2 clusters during the night, and that would allow us to cover the whole of the rotation period that we would expect to see, short to 1 or 2 days, as it were. Next slide. This is lithium depletion. The lithium depletion changes very quickly with age. In this under 200 mega years, it depends on mass, and so therefore how much the lithium is depleted allows you to find the mass. If we find there's no lithium, then it's stellar. That was the definition. That was how they recognized brown dwarfs. It's a secondary age indication. So if we look at clusters and we look for lithium, then the age should be the age of the cluster. The depletion should be consistent with the age of the cluster. Inside a cluster, the lithium, turning it around, becomes an indication of mass, because if the lithium is the depletion of the lithium will allow us to should change for masses, as we're saying. There is a dependence on both mass and age. So if we know the age, then therefore we can find the mass. This has been done with low resolution spectroscopy using LAMOST, so therefore well within the regime of what the WST would do. And it's very interesting, again, as a kind of another test within clusters. Next slide. The UCDs and brown dwarfs will be seen as companions when we start doing when the WST does it with its radio velocity capabilities. As you can see, the velocities, the radio velocities, are well within the extremes of the WST. It's kilometers, not meters per second, as you have to go for planets. This is the example that's being shown are 2 brown dwarfs where they are unresolved, and you see their orbits quite clearly. As I said, if you just randomly point in the part of the sky, there are only 20 UCDs, or let's say only 20, or on average 20 UCDs, but there are many stars, and the stars will have, by definition, lower mass objects if they're unresolved binaries. By definition, it will have objects with UCDs, so therefore we will have huge samples, and huge samples of binary systems have interacting constraints that will allow us to work really well on the astrophysics parameters. So we can see if the metallicity and the mass are consistent and the age are consistent, and it becomes more of a statistical sample rather than just right now we have various examples, handful of examples of various objects. Well, probably more than a handful now, but with the WST, just as a matter of its normal procedure when it's looking for other objects, if it adds these, it will discover many of these and will increase the samples. Next slide. So the thought that came to me when I was asked to give this talk was that the low mass objects can be piggyback objects on other programs, where WST is just doing whatever it does, and they happen to be in the field, and looking at clusters where the WST can probably sample a large part of the cluster. If there is temporal coverage, we can look for spectral change and variation. The lithium depletion requires just low resolution and signal to noise of about a 30. This is what's been done in the other program that I've seen. It's very important having the whole optical and NIR. For example, subdwarfs, if there are old objects, then the optical is very useful, and if there are young objects, then the NIR is very useful. So therefore, having the full optical to near infrared coverage of the WST is particularly useful for distinguishing the various indicators, that your favorite indicator that you might have. And when the WST, and perhaps I'm not saying it correctly, but when it's working in RV procedure, there will be huge samples of binary systems that will be discovered that will allow to cross checks of astrophysical parameters, ages, and eventually metallicity, which in UCDs, or especially in close to brown dwarfs, close to substellar, is really just hypothetical right now. I mean, there have been some studies, but it really isn't large scale in any way. The WST will allow that, and I think that's the last slide. Is it the last slide? Yeah. Okay. So
Yes, that's
I
it.
went